The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Well, this is one of my favorite lectures, and I could easily lecture on this subject for a couple of weeks. And I'm going to do it all in one day because it is atoms, and I think that it takes us a little beyond what is the appropriate level of this course. We want to be able to build some kind of a model that describes what we can see in the spectrum of many-electron atoms. And this will teach us useful things about how do we model the spectra of many-electron molecules, which in some ways are easier than many-electron atoms. So the way we first motivate the problem is for one-electron atoms, and there are two kinds of one-electron atoms. The really one-electron atoms, which are all like hydrogen and don't have any complexity. Then there's alkali-like, where there's one electron outside of closed shells. And then we split the degeneracy, say, of 3s, 3p, 3d. They're no longer degenerate. But we still have something that's really important, and that is one orbital, one state. And so because of that, it's really trivial seeing the periodic table in alkali-like spectra. You can ask, well, let's suppose we have potassium, calcium plus, or potassium, what's below potassium? Rubidium. I was going to say cesium, but it's rubidium. Okay, so what can we guess about the energy levels for first going potassium, calcium? Is it potassium or is it sodium before calcium?
No, it's potassium before calcium.
Yes, it is. Okay, I'm just checking if we got chemists in here or not. Okay, so here what we're doing is we're looking at the energy level structure of potassium, a neutral molecule, atom, and calcium ion. We know that the only thing that changes when we go from potassium to calcium is that the charge on the nucleus increases. So that means we expect that the energy levels will get farther apart. So that's pretty easy. And we can do much more sophisticated things already in freshman chemistry. Potassium to rubidium. Well, what's happened here? Well, the charge on the nucleus has increased a whole bunch, but we filled the shell, and all of the electrons that went into that filled shell are pretty compact. And so they shield pretty well. And so we have to decide, will the first excited state of rubidium be at higher or lower energy than that for potassium? Why is that a hard choice? Well, because the energy levels go as Z effective squared over N star squared. So N has increased when you go from potassium to rubidium. N star is probably going to increase pretty much the same way that N did. And Z effective is going to increase. And so these are going up together. And who wins? Well, you calibrate yourself, and once you've calibrated yourself once going down a column, you pretty much know that the first excited state tends to move down a little bit. That's a harder decision than the first excited states moving up a lot as you follow an isoelectronic rather than an isovalent sequence. But that's it. That's all there is. if there were only one orbital, one state.
Is it clear that going from potassium to rubidium is a similar thing from going from calcium plus to strontium plus?
Yes.
Why is it absolutely clear that at some point M star could dominate over, that they could switch if you just make M star bigger?
Okay, what you would do is you'd build a model. You'd say, okay, as we fill a shell, the charge on the nucleus has gone up, and the shielding due to the filled, each electron gets a certain fractional shielding. And so you can build a model that ought to fit essentially all of the isoelectronic molecules. So you could do potassium, calcium plus, scandium 2 plus, et cetera, as you go across. And you'd build a simple model, and you'd have also want to describe. So if anybody's outlier, you say that's either interesting or wrong. The ideas are, we have orbitals, and they are shielded by all of the filled orbitals, and we're only putting one electron in an open shell, and as a result we have really simple stuff. Unfortunately, for atoms and molecules, the world does not consist of one-electron systems. It's many-electron systems, and we somehow have to deal with that. And so the framework of this lecture is to show how do we build an effective Hamiltonian which describes the electronic structure of many-electron atoms. And these provide us with guidance for what we are going to experience when we build effective Hamiltonians for the electronic structure of molecules and effective Hamiltonians in general. Okay, because the problem is calcium, neutral, has an electronic structure where we know that the lowest electronic configuration is 2 electrons in s orbitals. And then it has 4s, 4p, and then there might be a higher, there are going to be higher configurations. This is easy. This just gives rise to a singlet s state. This gives rise to a singlet p state and a triplet p state. How do I know that? Well, that's the subject of this lecture. But the low-lying, instead of one orbital, one state, we get a configuration, several states. And suppose we go to scandium, well, then we might have 4s d squared or 3d squared or something like that. And let me tell you, d squared gives rise to singlet g, triplet f, singlet d, triplet p, and singlet s. So it gives rise to all of these states. And each of these states has spin components. So what do we do? How do we, where is periodicity? How do we begin to understand how to make comparisons between calcium and scandium when we don't even know what the metric is? We don't know what to look at. What do we get when there's many states coming from a configuration? How do we decide how to impose periodicity on what? So we need a model where the parameters in the model are interpretable, have the periodicity that we can understand based on shielding and trends in sizes. And this model wants to be both qualitative and quantitative. Now this is really important, and as soon as you start looking at tables of atomic energy levels, you say, this is really awful. This is, how could anybody make any sense out of this? Yes, maybe I could assign the spectrum, but is it interesting? Is there anything that I can glean from these patterns? Well, one thing you might do is say, okay, I can probably develop some rules, they're called Hund's rules, which once I write down a configuration, I can write what are the LS terms, that's what they're called, that arise from that configuration, and of those, which one is the lowest? And of those, of the lowest one, which J is the lowest? So those are the Hund's three rules. And so you could say, well, I'm going to try to impose periodicity by just deciding what's the lowest energy, LSJ, energy level of a configuration. Well, that wouldn't get you very far, because sometimes the LSJ terms are very widely spread, and then the next one they're not so widely spread. It might be sensible to say, okay, I've got a configuration. Let's calculate the degeneracy weighted average energy of the configuration. But that requires knowing a lot. And often, all states of a configuration aren't observable. So that's not a good thing either. So what we need is a way of describing the states of something that's just a little bit complicated in terms of parameters which we can understand. And this is why I love this lecture or this topic, but I can't do justice to it because if I did, you would probably all need to spend a week at McLean's. All right. So let me give sort of an outline of what we do. We take an atom, and we would do the same thing for a molecule. I just haven't taught that to you yet. We know what the atom is, and we write the list of orbital occupancies. We know how to do that from freshman chemistry. We know Aufbau. And so, we can pretty much guess the orbital occupancies of the lowest lying state of any atom. And that's called the electronic configuration. And you could also write configurations that are likely to be excited but relatively low-lying. And you're going to want to do that anyway, because if you're going to be observing a spectrum, you're going to be observing transitions between states belonging to two different configurations. And so you're going to have to somehow use freshman chemistry ideas to say, okay, we have this configuration and this configuration and this one and this one. That's probably enough to figure out what's going on. Okay, once you have that, you want to know what LS terms arise. And this is a topic that is usually taught in an inorganic chemistry course. And it's taught in a very obscure way. It says, this is what you do. Why you do it? Well, I can't tell you that because that's such an advanced topic, but I'm going to test you on it. And you're going to have to learn this method of ML-MS boxes. And that bookkeeping method, which maybe most of you have seen, but not everybody, that it used to be always taught, even in quantum mechanics courses. But 30 years ago, it's dropped out of quantum mechanics and was left in inorganic. I don't know what you've seen that in inorganic, right? Yeah. And probably everybody has. So what is this? Well, what's going on here? ML is the eigenvalue associated with the operator Lz, and Ms is the eigenvalue associated with the operator Sz. And L squared, Lz, S squared, Sz are a mutually commuting set of operators, which also commute with the electronic Hamiltonian, but not the spin-orbit Hamiltonian. So that means that we can write basis functions of the electronic Hamiltonian that are expressed in terms of the quantum numbers associated with the eigenvalues of these operators. That we can label things. And so what we're doing is we're somehow discovering some good quantum numbers, ML, MS, L, and S. They're good enough, excluding spin orbit, that we can simplify the electronic Hamiltonian. And we know that little m sub L and little m sub S and little l, those are not good quantum numbers of the electronic Hamiltonian because of our friend 1 over Rij, the interelectronic repulsion. And I could say a lot about this, but I think I shouldn't, because I think I want to give you the big picture. But you know, you've got me here. You know, if you want to ask questions, I really know more than probably anybody at MIT about atomic structure and how you reduce that to many-electron, to effective Hamiltonians. It's just not taught anymore. Okay, so if we look at the possible values of m sub L, and m sub L is the sum over electrons of little m sub L. And so if I say we have a configuration d squared, well, d can have m sub L 2, 1, 0, minus 1, minus 2. These are the possible values of m sub L. And m sub S can have values plus a half and minus a half. And so these 10 symbols correspond to labels of spin orbitals, which are basis functions, which are our basis functions. So everything is going to be expressed in terms of states involving 2 of these at a time, because we say it's d squared. So we have to pick 2 of these. And if you pick 2 of these, you immediately know m sub L, capital M sub L, the total number, the total projection of the orbital angular momentum on Z, and m sub S. Any 2. And so that says, well, so why don't we do that? Then why don't we just somehow pick the various possible combinations of these? And we know, okay, we got 10 of these. And how many combinations can there be? Well, there's 10 times 9 over 2 because of the exclusion principle. We don't know what the, you know, in inorganic chemistry, when this is taught, the exclusion principle is basically said you can't put 2 electrons into the same spin orbital. That's it. But there's something deeper behind that. But anyway, you know how to calculate the degeneracy. 10 choices. One's used up, now 9 choices. Didn't matter which order you filled it, so 45. There are 45 possible m sub L's and m sub S's. So we do this silly game of ML, MS. And we could be really anal about it and go from the maximum possible value of m sub L, which is 4, down to the minimum possible value, which is minus 4, and m sub S from 1 to minus 1, and there would be 45 boxes to fill in. But we're told, don't do that. Just take one of the, take the, this subset 4, 3, 2, 1, 0, and fill out that corner of the table. That's going to be enough. And then there ensues the magic crossing out of boxes. And from that, you determine the allowed values of m sub L and m sub S. And I just can't believe that this has been taught to almost every chemist for 100 years, and nobody understands what this is. And I hope that when we're done, you will understand. Okay. Because L squared, LZ, S squared, SZ commute with the Hamiltonian, the electronic Hamiltonian, it says that there are going to be states labeled by the quantum numbers associated with them. And if we're entitled to have a particular value of L and S, then there are going to be 2L plus 1 times 2S plus 1 states associated with it. You're going to get the full LS term, not a part of it. That's a little harder for me to bullshit around, but it's true. You're entitled to get them all, and that's why this method of boxes works. But it's a lot of work for very little, because you really do want to know what possible LS terms arise, but you could also look them up in Condon and Shortley or Tinkham or some book. And after a little bit of looking at this, you can get the idea that as long as you have no more than 3 electrons or 3 holes in a particular shell, you can figure it all out. And if there's electrons in different L's, that makes it easier rather than harder. So it's not a big deal. You could probably learn that better than this method of boxes, which is something that occupies space in your brain that could be used for other things. Okay, so we have this method of boxes, and we find out what the L's and S's. For molecules, you have to do the same sort of thing, but the worst case you have for a molecule is an orbital that can have 4 electrons in it, pi orbitals or delta orbitals. And since holes are equivalent to electrons, the worst case you'd ever encounter would be delta squared or pi squared. And that's easy. So the stuff we do with atoms is a lot harder than what we do for molecules. And so there are just a few things you need to remember, and you've got this completely knocked. Okay. So we can work out for a particular configuration what are the LS terms. And then our job really begins, not ends, as it does in inorganic chemistry. In inorganic chemistry, you do this and you say, okay, which is the lowest one? And now we'll stick it into an octahedral or a tetrahedral environment, and that'll split according to ligand field theory, and that tells us the electronic structure that we care about. So all this work to determine a few low-lying states, and okay, but we don't do that. We're not going to put this in a lattice or anything like that. It's in the gas phase. Okay, and we would like to be able to describe all of the energy levels of the states that come from a particular configuration. So the method of boxes tells us which LS states, but what we really want is how to write things like this as some kind of linear combination of the terms that are in the boxes, the pairs of spin orbitals. Now we get the exclusion principle. The Pauli principle says that the wave function is antisymmetric with respect to permutation of any 2 electrons, because electrons are fermions. This other thing is just a special case of it. And so how can we possibly write a wave function which is antisymmetric with respect to all pairs of electrons? And the answer is, stupid, write a determinant. Because you permute the rows and columns of a determinant, it changes sign. That's what we mean by antisymmetric. And so we get what are called Slater determinants. And if I'm not mistaken, this room was probably Slater's office a long time ago. He was an MIT faculty member, and he did hang out in these parts. It could have been his office. And but anyway, a Slater determinant. So a Slater determinant is just an antisymmetrized collection of spin orbitals. And we label it if it were p squared, we would label it, say, 1 bar, double bar. So that would be m sub L of 1, m sub L of 1, m sub s of half, m sub s of minus a half. So that's ml2, ms equals 0. So that's a Slater determinant. And so that's a basis function. And we would like to find what linear combination of these guys makes these guys, because these are much more useful than these. However, these are really useful for evaluating matrix elements of operators. But these are useful for applying symmetry. Now, before I get too far gone, there's this wonderful book, Group Theory and Quantum Mechanics by Michael Tinkham. And there's pages 154 to 188 gives you all of the algebra that I would develop in the 4 or 5 lectures on this subject. And it's really beautiful. It's hard, but it's not as hard as some other presentations of it. And this is a wonderful old book which I learned quantum mechanics from. Okay, so we want to find the correct linear combination of these guys that makes these guys. I'm not going to tell you how to do that. You don't really want me to tell you how I do it, because there are powerful methods involving angular momentum coupling coefficients, 3, 6, 9Js, which is the way you do it, especially if you were going to use a computer program. And there's raising and lowering operators, which is the way I do it, which had been a nightmare. First-year graduate students taking my quantum mechanics class for 25 years until I was kicked out of the course. No longer allowed to teach that course, probably because of the way I do all this atomic physics. Okay, so once we can find a way to write these things as linear combination of these things, then we're in a position to evaluate matrix elements of the terms that make up the Hamiltonian. So the Hamiltonian involves let's just call it this, this, and this. So this is, some sort of orbital energies. It's kind of a Hartree-Fock thing that decides what the energies of each orbital will be depending on what the states of the other electrons are. So we could say, okay, that is expressed in terms of orbital energies, and maybe there's some hidden complexity because the energy of an orbital depends on what other orbitals are occupied, because we know about shielding. So we have to be a little bit, complicated about this. So we have orbital energies. And this is the interelectronic repulsion. And this is expressed in terms of what are called Slater-Condon, or Coulomb and exchange integrals. These are 1 electron. These are 2 electron operators. This is a 1 electron operator. That's easy. Matrix elements of 2 electron operators is why this topic takes 4 or 5 lectures. But it's a very valuable thing to know how to evaluate matrix elements of 1 and 2 electron operators in a Slater determinantal basis. It's neat, it simplifies things, and I recommend it, but I'm not going to teach it to you because that would really be taking advantage of your credulity. And then there's the spin orbit, which is expressed as some sort of an operator. And so this is a 1 electron operator. It's a sum over the individual electrons or orbitals. L dot S, well, you know what to do with L dot S in a basis set in which you've specified M sub L and M sub S, or L and S and J. So this operator is pretty easy. And okay, and so these are the three things that you need in order to describe the energy levels. And so this, and zeta NL is where the periodicity is. Your ideas for how do properties of atoms vary as you go across the table, it's all written into these parameters. If you look at a table of values of orbital energies, the interelectronic repulsion, Coulomb integral and exchange integral, the spin orbit integral, they all can be understood in a simple framework. And that means you could also represent all of the electronic states of all atoms by doing some kind of a least squares fit to some data fitting these parameters, and then you generate everything. And this is actually quite wonderful because not only does this present the periodicity, it also enables you to calculate everything that you could possibly observe. Transition relative intensities, patterns of energy levels. It enables you to do wonderful things. But the important thing is what we learned in freshman chemistry about the periodic table is all written in these parameters. And you can understand them. And I consider that to be really beautiful, but I'm strange. Okay, so now let's go to page 4 of the notes. And I'm just going to talk you through a lot of the qualitative stuff. Yes?
If you have one more copy of the notes, can I have? If you don't have it, okay.
There you go. Okay. Okay. So, all right. So on page 4, there is a little table of the states that arise from the various number of electrons in d orbitals. It's really simple for S. It's really simple for P. It's pretty simple for D until you get to 3, 4, and 5 d electrons. There's this wonderful thing that electrons and holes, as far as this algebra is concerned, are the same. And so if you work out D1, you have D9. If you work out D squared, you have D8, and so on. And the only thing that's different is the sign of the spin orbit constant, or the sign of the spin orbit when you've done stuff. And there are other things about half-filled shells and half-filled subshells that appear when you start doing ligand field theory on these things. So what you see is there's 10 of these, there's 45 of these, there's 120 of d cubed, 210 of d fourth, and 224 of d5. Why would you care? Well, it gets complicated. And wait till you get to F. Because you can always get up to F7 and you could calculate what F does. It's terrible. It's just frightening. Okay, so there are lots of states, but then there's rules for what is lowest. And since most spectroscopies bottom up, we do care about what is the lowest state of each configuration. And there are 3 Hund's rules that tell you what is the lowest state of each configuration. And they tell you nothing more than what is the lowest state of each configuration. They don't tell you anything about the order of the states other than what's lowest. And there are many people and many textbooks who have that wrong. And so what is lowest? Maximum spin. Of those, the one that's lowest is maximum L. That's one state. Maximum L, maximum S. Nothing about the ordering of states. If you don't have the maximum L and maximum S, well then the maximum S but a different L, well that might be low-lying and might not. It doesn't tell, Mr. Hund doesn't tell you anything about that. And I can derive, where these come from. And of then, you have maximum L, maximum S, which J is the lowest. And if you have a less than half-filled shell, the lowest possible J is lowest in energy. And if you have a more than half-filled shell, the highest possible J is lowest in energy. And if you have a half-filled shell, there isn't any spin orbit splitting. So that's a little bit beyond the Hund's rules. So there are 3 Hund's rules, and they tell you what is the lowest state of a configuration. So that's going to tell you what's the ground state, and it's probably going to tell you what are the allowed transitions to the lowest state of each configuration that would enable you to begin to know the electronic structure of the molecule. So it's really important, Hund's rules. Okay, so we know how to represent all of the states of all of the low-lying configuration in terms of these orbital energies, the Coulomb and exchange integrals to electron, and the spin orbit. And so we need to write an effective Hamiltonian now that will generate the actual energy levels and eigenvectors that will be what we encounter in the spectrum. So in the spectrum, we see energy levels, and we work backwards to get these things. But if we haven't recorded a spectrum, we use periodicity to make good guesses of these things, and then we attempt to make sense of what we're going to observe in the spectrum. And since I'm a professor, I don't encounter the spectra. I encounter other people's analyses of the spectra, and then I make comments on whether they're right or not. But I don't analyze spectra. I really am interested in the Hamiltonian that represents them. Nice work if you can get it. Okay, so on page 5, it's illustrating periodicity in a beautiful and subtle way. This is a figure from Tinkham. There's a similar figure in Condon shortly. And so this is X, the number of d electrons. And this is the spin orbit. There's 2 different things plotted here. One plotted here is something that's going up like that. And another thing that's plotted here is something that's small, crosses through 0 and gets large, 5. This is the 1-electron spin orbit parameter, which has to increase monotonically because it goes as z to the 4th. As you make the charge on the nucleus larger, the next electron always sees a larger z effective, because the previous electron didn't shield perfectly. So you get that. And this is what you expect. And it's beautiful and it's monotonic. This is kind of ugly because it changes sign and it's got a lot of curvature. This is the spin orbit constant associated with the lowest energy LS term. And so the lowest energy LS term of a particular configuration varies in a peculiar way as you add electrons. And when you get past half, it changes sign. And so this sign change is the kind of thing that you'd really not like if you're having a model, because most models like to be monotonic. And so this is already concealing the hidden beauty of this periodic trend. You can capture it. But anyway, this is when you look at either the spin orbit coupling constant of the d electron or the spin orbit coupling constant of an LS term. They're different things. You get these 2 different regular curves. Okay, now we're going to go to page 7 where the rubber hits the road. Okay. when you are dealing with Slater determinants and you want to evaluate matrix elements of 1 and 2 electron operators, there's an algebra that you have to learn how to do. The algebra is a little bit complicated, and I don't want to teach it to you, but so you do this algebra, and the interelectronic repulsion effective Hamiltonian for p squared can be written in terms of the F's and G's. It turns out you never get any G's if you have two identical electrons. You only get G's if you have, say, an S and a P, or a P and a D. So there's no G's in this matrix on the top of page 7. It's just expressed in terms of F0 and F2. Okay, what's this? This is if the electrons are p electrons, the maximum index you can have is 2 times 1, 2 times L. So if you had F electrons, you'd have F0, F2, F4, and F6. Okay, so, but since it's only P, you have F0 and F2, and so what you end up is you write down matrix elements of the Slater determinants, and you discover that this guy is diagonal, and you discover that, let's just write these are the LS states that you can have for p squared. And this is a 1 by 1, this is a 1 by 1, and this is a 3 by 3. And so there's a number that goes here, a different number that goes here, a third number that goes in all 3 places here. So the electronic structure is determined by the interelectronic repulsion, and we have an energy for the singlet S state, for the singlet D state, and for the triplet P state. And we get that by just evaluating matrix elements of 1 over R, 1, 2 in the Slater determinantal basis, learning the algebra to do that. And if you're a theorist, you'll learn that. If you look at Tinkham, you can learn it. And some of you already know it. Okay, so this Hamiltonian is fully diagonal. And you say, oh, hooray. I don't have to do any work with a diagonal matrix. Unfortunately, you almost always have to deal with spin orbit. And the spin orbit matrix is not diagonal in the usual basis. So spin orbit so the spin orbit operator has the form zeta Li Si. And you can prove that that is a scalar operator with respect to big J. And because that's a scalar operator with respect to big J, it has only delta J equals 0 matrix elements. And the matrix elements are independent of M sub J. So we can use this to simplify the spin orbit matrix element matrix if we write it in either the L, S, J, Mj, or J1, J2, J, Mj basis. Okay, so this is the basis we like because that's one of the ones we used for this. This is a little bit problematic because we have to do a transformation from this angular momentum function to this one in order to use this for a spin orbit. And now, why would we care about that? Well, it's because spin orbit is a one-electron operator. It's diagonal in J1, it's diagonal in J2, it's diagonal in J. And so if we use this basis set, spin orbit is fully diagonal. But this is not. If we go to that basis set, we spoil the diagonal nature of this. If we work in this basis, we don't have any trouble writing down the matrix, but it's not diagonal. So at the top of page 7, what time is it? Am I done? Am I out of time?
It's 5:48.
Oh, I got enough time to talk for another 10 minutes or so. Okay, so at the top of page 7, you have the spin orbit Hamiltonian, and it's a bunch of 2 by 2s because you notice that there's 2 j equals 2s, and there's 2 j equals 0s, and 1 j equals 1. So we have a 2 by 2 for j equals 2, a 2 by 2 for j equals 0, and a 1 by 1 for j equals 1. And so if we take the spin orbit and interelectronic repulsion matrices and combine them, we'll get a 2 by 2, a 1 by 1, and a 2 by 2. And nobody has trouble dealing with a 2 by 2 matrix. We know how to diagonalize it. Now, in case you have forgotten, if you have a 2 by 2 matrix, it has this form, and it's always useful to replace it by E bar 0, 0 plus delta over 2 minus delta over 2 v v. Because this is diagonal, that's just taking out the center of gravity. And this has a secular equation that is so simple, the energy levels of this are just the square root of delta squared over 4 plus v squared square root, plus or minus. So this is, as soon as you have a 2 by 2, you know you're going to be able to get to this, and then the problem is solved. So all of these matrices can be then written as, so you can find the eigenvalues, you can find the eigenvectors, and you've got everything. Are you all with me on this? Okay, now, I think the last main point I want to make is we have 2 basis sets. One in which the spin orbit is diagonal, and the other in which the electronic term is diagonal. And that's typical of what you encounter when you do effective Hamiltonians. You generally have two physical effects. One, and they oppose each other in the sense that one likes a particular representation, the other likes the different representation. In representation number 1, one operator is diagonal and the other is off diagonal. In the other representation, it's the other way around. It's like, an incompatible relationship leading to a divorce. No matter what you do, you can have eigenvalues, but you can't have a simple representation. So, and it always happens that there is a term that one term always opposes another, and sometimes you play favorites. You say, I like spin orbit, and so I'm always going to choose the spin orbit diagonal. And sometimes that's good and sometimes that's bad. And so this nice figure that I worked so hard over the years on page 8, this illustrates the qualitative energy level structure for p squared in the zeta equals 0, f2 not equal to 0 limit. And here is in the F2 equals 0, zeta equals not equal to 0 limit. And so what I did is I kept energy levels, and then I normalized by dividing by the extreme, the energy difference between the top and the bottom, so that they could be put onto the exact same scale. So you see, in one case, we have a pattern of 3, degenerate, 1 and 1, and over here we have a pattern of 2, 2 and 1. This is the LS. This is the LS limit, where spin orbit is not important, and this is the JJ limit, where spin orbit is so important that the interelectronic repulsion is not important. You rarely get to this limit except when you get into the very bottom of the periodic table, where spin orbit is big compared to interelectronic repulsion. And that's partly because spin orbit is big, and partly because the orbitals have gotten so large that they don't repel each other anymore. So, but these are two very different patterns, and you're sort of alert for these in the spectrum. That tells you what are going to be the good quantum numbers. It tells you something about relative intensities. It tells you what pattern, what part of the pattern do you need to see to figure out what states you're in. The next lecture is going to be an elementary lecture on how do we assign an atomic spectrum. Never will you find anything in any textbook except in Hertzberg's little book on atomic spectra, where it describes how do we assign a spectrum. And so it's something you have to do. And so I will talk about it, but I use these kinds of patterns as well as some simpler ideas. And so
is there any connection between the energy splittings that you wrote here, like 6F2, 9F2, and...
What page are we on?
This is page 8?
Yes.
Is there any connection in the zeta equals 0 and the zeta does not equal 0 limit between the energy splittings of the core structure?
Well, if I've chosen the two limits that are perfectly in one,
For the same,
I've chosen it for p squared.
Right.
And so these patterns, there can't be any resemblance between the two patterns because they're determined by two
completely different. Yeah.
Right. But what you can see is on the next page, I describe the energy level patterns in the extreme limits and for two real atoms in between those limits. And so you can see how as you go from the spin orbit is 0 to the spin orbit is small limit, the pattern is still clear. You just split the spin orbit, the triplet p state, which is the lowest state because of Hund's rules. And then as we go up in spin orbit coupling strength and down in interelectronic repulsion, we see that the J equals 0 levels repel the daylights out of each other, and the J equals 2 levels also try to repel, and eventually you end up with this pattern where now you have the JJ limit, where all that matters is the two J values of the two electrons, and it doesn't matter that 3/2 plus 3/2 can make either 0 or 3. Well, that's interesting. Well, they can make 0 or 2 because of the, it's true. It's not a mistake. It was a mistake here. On the previous page, I explained how the exclusion principle knocks out something. But anyway, so you get a pattern of 2, 2, and 1, and it just has to do with the spin orbit not changing J for individual electrons, but it will change J, it will change L and S, but not J for the overall. So, and you can write, as you can always do in effective Hamiltonian land, you can write the effective Hamiltonian, either the LSJ or the JJJ limit. I don't know, the English language is defective. There's no different tone for uppercase and lowercase letters. So JJJ sounds really stupid, but it's really referred to as JJ as opposed to JJJ. But anyway, that's all I have to say, I think. And I do have a suggestion. This is not required. However, I do recommend that you go through the algebra that's on pages 5 through 11 for p squared to do d squared. And all of the critical stuff you will be able to find in Condon and Shortley or Tinkham. It's in the, this is not an assignment. I do recommend it. If you're going to learn this material, it's a good idea, but it's not as important as some of the other stuff that I will deal with. Okay. You missed Nocera's lecture. You had to listen to me. I don't know whether that's a plus or a minus. But anyway, see you on Wednesday.
Can I ask a question?
Sure.
Let's back before. The first thing you do is you list the orbital configurations.
Yes.
And then you calculate these. Okay. Freshman chemistry ideas get most of the orbital configurations right for atoms, but maybe not technetium or some other weird transition metals. For molecules, it can also be occasionally difficult, right? And so, of course, we can also, we also know, because we have books and other people have done experiments, and they're sometimes more sophisticated, here's what they really are.
Well, usually what happens is when you do these sorts of things, you know the trends. And so there are, like your friend, there are known unknowns and unknown unknowns. Well, when you have two things pointing in the same direction, it's always easy to make a deduction. When they're pointing in different directions, it's much more subtle.
You need to actually calculate numbers.
Sometimes you have to calculate, but usually you can say, well, this is interesting because there's a delicate balance between these two symmetries, and if we look at a series of isoelectronic molecules, it might switch. As it does, actually, for the alkali oxides. The alkali monoxides, you would naively predict that there's a doublet pi and a doublet sigma state, and their relative order reverses as you go up the periodic table because there's an overlap repulsion effect and a quadrupole effect, and they go in opposite directions. And so you can understand it. But usually, when you know you have opposite effects, you have to find some reason for deciding which one's going to win. But very often you know that they're both going in the same direction.